This talk is Atomic Security Analysis of IoT Firmware. And the speaker is Matt Brown. A few announcements before we begin. We want to thank our sponsors, especially our inner circle sponsors, Critical Stack and Veil Mail, and our seller sponsors, Amazon, BlackBerry, and Microsoft. It's their support along with our other sponsors, donors, and volunteers that make this event possible. For cell phones, these talks are being streamed live, except in Underground, which this is not. And as a courtesy to our speakers and audience, we ask that you check to make sure your cell phones are set to silent. And here's Matt with his presentation.
All right. Can everybody hear me? All right. My name is Matt Brown. And today, I'd just like to thank you all for coming out to my talk. Today I'm going to be talking about ByteSweep, which is a free software IoT security analysis platform. So a little bit about myself. I'm a Christian, I'm a husband, and I'm soon to be a father, and then I'm a hacker. So when I'm not busy doing those first three things, I love to tear apart IoT devices and see how they work and just tinker with stuff. And so today, what we're going to talk about is I'm going to kind of lay out what I think are some of the big problems that exist in the IoT security space today. Then I'm going to discuss some of the automated analysis techniques that I've built into my platform, ByteSweep. Then we're going to do a quick overview of the architecture, the system architecture of ByteSweep and some of the deployment methods. Then we're going to give a demo, and then I'm going to talk about some of the things I want to do with this tool moving into the future. About a month ago, this news story landed in my news feed, and I thought it was pretty interesting and pretty relevant to what we're going to be talking about today. So way back in 2017, the FTC sued Dlink over a number of vulnerabilities in their routers, and there's just a couple of quotes from this article that stood out to me. So the first one is that one of the things the FTC cited, among others, is that Dlink repeatedly failed to take reasonable testing and remediation measures to protect hardware from well-known and easily preventable software security flaws. So these weren't these crazy advanced, nation-state level attacks. These are really simple, easy to find, easy to remediate things. And then as a part of the settlement that Dlink made, they agreed, among other things, to perform testing for vulnerabilities before releasing products. That's a novel concept, I know. We're going to jump into just some of the things that I think are the reasons why we struggle with security in the IoT market. So the first one is that security costs money, right? And in much of the IoT space, these device manufacturers are operating on razor-thin margins to the point where they don't have the budget, right, to pay that full-time security engineer to be on the product team, or they don't have the funds to pay for that big external pen test from some big company. The other thing is that there are a lot of complex supply chain dynamics that exist in the IoT space. Oftentimes, when you take a look at one of these devices, you'll see that it was built, the actual hardware and a lot of the software was built by a hardware manufacturer. That was then passed downstream to some system integrator that wrote some extra APIs and slapped it on top of that device. And then oftentimes they'll pass it on to another company that just white labels it. They just slap their logo on that device, and then it finally ends up in a consumer's hands. And so the thing that happens is in each stage of that supply chain, source code rarely, if ever, gets passed down, because that is the proprietary technology of the company that's upstream from them. And so if you haven't watched Dan Kaminsky's keynote for the first DEF CON China, not the one like this recent year, but 2 years ago, he told this really cool story about when he wanted to go do an audit of a solid state drive manufacturing plant. And he went in and met with the people there, and he asked them, hey, can you just hand over, like, just give us all the source code for everything that runs on this solid state drive, and we'll do a security audit. And the guys kind of laughed at him and said, hey, you think we have all that source code, right? And so one of the quotes from the talk is he said that each one of those companies, they passed a binary blob down that supply chain onto the next so that they wouldn't be factored out of the manufacturing equation, right? This is like, these people hold on really tightly to their IP, and so any kind of security analysis that we perform, we can't rely on source code tools in this space. And then the last problem, this is certainly not a problem that just exists in the IoT space, but it's very pronounced in the IoT space, is that security is an afterthought. So if you do perform a pen test at these companies, it's conducted right before going to market, and that means that if they find some really simple vulnerabilities, let's say they find a piece of software and they say, hey, it has version 1.0 and you need to upgrade to version 1.1 in order to be secure, okay, maybe they'll do that right before they're going to market. But if the pen testers come back and say there are some big design flaws that we've found, oftentimes those risks are going to be accepted and it's just going to be sent to market as is. So what does a solution to this problem look like? And one of the things I've really enjoyed about this whole track today and being a part of it is that I think there's this sense of camaraderie where we all want to come together and solve these problems together. We understand that no one person is going to solve it by themselves. And so this is just my shot at solving this problem. But I really want to hear from you guys what you think your solutions to these types of problems are. So for me, what a solution would look like is free and open source software, right? Because we established that a lot of these companies are operating on these razor thin margins. The solution is going to provide automatic analysis because we can't pay, a security engineer full time to run a bunch of manual testing. And then it's going to utilize static methods that don't require source code because we don't have the source code when we're performing these audits. So that's where my tool ByteSweep comes in. And so ByteSweep is a web application that is written in Flask on the front end, and then there are a number of Python backend workers that do a lot of the heavy lifting, the analysis. These are licensed under the AGPL and the GPL respectively. And if you're like me, when you have somebody giving one of these talks in their software project, I'm just like, hey dude, show me the code. So feel free to browse the repository. This is public as of this morning. And you can just check out the whole project. So now we're going to jump into some of the automatic analysis techniques that I've implemented into the ByteSweep platform. So the first thing that a user of this tool would do is they would come to like the upload an artifact page and they would upload whatever they want to be analyzed. This most likely is going to be an entire IoT firmware image, but it doesn't have to be, right? If you're just interested in a subset of files, you can wrap those up in a zip file, upload it. Or if you're just like, there's one binary on this device that I really am interested in, you can upload that one binary and it'll analyze that alone. So after we upload a binary, or after we upload an artifact to the platform, we then need to extract all the files and file systems that we can out of that image. And so to do this, we use the tool Binwalk. Binwalk, if you've worked in IoT firmware analysis, it's kind of like the go-to tool for unpacking firmware. And it has a Python library. Binwalk's written in Python, and it has a really good set of Python APIs. And so that works really great for me. So this tool is so awesome, but that means it's like even more unfortunate that the developer of it has decided to stop development on the open source tool and instead is kind of pushing this proprietary cloud-based service. And so this is kind of too bad, but what I want to do to deal with this is just to fork this project and to continue fixing bugs, developing new features. And so underneath the ByteSweep project up on GitLab, I've got ByteWalk. So that's going to be the name of the Binwalk fork that I'm going to be supporting going forward. But Even though it's like sad to see like what's going on with Binwalk, I still want to thank like DevTTYS0 for all of the contributions that he's made to the open source community. Like this whole project wouldn't be possible if it weren't for all the work that he put in. And so just got to say thanks to him. So after you've uploaded a firmware image to the platform, it's tried to extract all the files and file systems that it can. Then we need to kind of enrich that data a little bit. So there's two big data enrichment things that the platform will do. First is we want to determine what type of file a given file is. And so for that we use libmagic. If you're not familiar with libmagic, anytime you run the file command on any Linux or Unix-based system, this library is the brains behind that. It's basically looking at the file, the first few bytes of that file, and then it's doing a lookup in some big database, and then it's going to tell you what type of file that is. And then the second calculation, or the second piece of data enrichment we do, is a byte level Shannon entropy and an index of coincidence calculation. So these are more of like the heavy like math-based things that are going on. And so the cool thing that you can do with like byte level entropy is that you can actually determine if a file is encrypted or compressed. So this is an example from the graphical interface. We can see that a Shannon entropy that's really close to 1 is going to like kind of warn the user that this file is likely either encrypted or compressed. Can't necessarily distinguish between the two, but it's one of those. So then after we've enriched that data, there's a number of data analysis techniques that are implemented in the ByteSweep platform. So the first one is that we're going to take any files from that data enrichment step that were determined to be either a binary executable or a shared object library file, and we're going to search for unsafe C functions. So as an example, you got like your string copies, your strcats that are going to be potential risks for buffer overflows, and then you have your system calls, your p-opens that are going to be potential risks for command execution, right? The existence of these functions doesn't like necessarily mean that a vulnerability exists, but it's just telling you that there's a risk. And then if you're a pen tester using this tool, you're going to use that as like a jumping off point to, this is where I want to look inside of this binary to see if there is actually an exploitable vuln. So to do all this, the platform uses Radar2. If you haven't used Radar2, it's a really awesome open source reverse engineering tool. And it also has a awesome Python library called R2Pipe that lets me programmatically search through a binary for function references like this. So for the next few analysis steps that the platform will do on all the files, I got to talk first about this regex search system that's implemented in ByteSweep. So basically, the whole point of this search system is to look for any kind of static string content that we deem interesting. And so these regex rules that we can kind of see an example of one at the bottom here are all built into this YAML config file. And it lets users write new definitions for things that they want to look for inside the binary file or inside those strings. And then the platform will find those things. And then it'll tag it as a certain type of finding. So in this case, we have a rule that is a regex expression for a standard like Unix shadow password hash. And so it's marking it as a type of password. That's the like finding that it's gonna mark it as if it does find anything that matches this expression. And if you're interested in like contributing to the platform, there's documentation up on GitLab to tell you how to create some of these more advanced regex rules. So with that regex search system, right now the platform is looking for 3 big things. So the first one is password hashes, saw an example of that. And then things like hard-coded keys. So you got your RSA, public and private keys, open SSH keys, things like that. And then the other thing that it looks for is third-party component strings. And so a third-party component string is a string inside of an open source library that is going to indicate to us what its version is. And so with these like regex rules, we can actually identify whether a given file that's been extracted from the original artifact, whether it's like you can determine if it is a certain program and version combination. And so with those, so if you were here for the previous talk where Alan Friedman talked about software bill of materials, this is what I'm hoping is like a start to moving in that direction to be able to automatically identify and build out this software bill of materials. And he actually talked about a couple of like standard data types that I hadn't even heard of before the talk. So definitely plan on implementing those as like an export, feature inside my tool. And then the last thing the last analysis step that's taken by the platform. To understand that, I got to explain these two different services that run inside the platform. The first one is the CVE fetch service. So this is a service that syncs the National Vulnerability Database's JSON feed of every CVE that's ever existed down to a local database on the platform. And then the Watchdog service, this service's job is to then cross-list those third-party component program names and version strings with all of the data in the CVE database. And so this is an example of like a part of a CVE out of that JSON feed. So we can see here under the product name, it's saying OpenSSL, so that's the name of the program or library. And then it has a really well-structured way of saying which versions are affected by the CVE. So with this version data here, we can then perform a cross list of everything that we found inside of the firmware image. And the cool thing about this service is that it doesn't just do it the first time it uploads it. So if I upload a piece of firmware today that isn't vulnerable to anything, but then a new CVE comes out, it's going to automatically update the list of CVEs that are affected. So now I'm just going to give a little quick high-level view of the architecture and some of the deployment methods, and then we're going to jump into a demo. So the back end is all Postgres. This is for some of its useful like JSON-B data structures that are really nice for dealing with JSON. The web interface, like I said, is a Flask front-end interface. And then you have those three back-end daemons that are also written in Python. The worker, again, so the worker's job is to do most of the data analysis. And then you have the last couple bits of it that are done by those other services. And for deployment options, so right now the build system for ByteSweep builds deb files that target Ubuntu Server 1804, and it builds RPM installer files for CentOS 7, and then you can also, I've got Docker images for everything, so it can also be deployed fully via Docker. So now I'm going to jump into a demo of the tool. And so this is the web interface that a user of the system would interact with. And so they can either list, previous artifacts that they've previously submitted, or they can add a new one. This is what the upload an artifact interface looks like. It's pretty simple. We're just going to look at one that has already been analyzed for an unnamed camera root file system. And so here we can see that it extracted a number of files out of that file system. There's no encryption keys in this one. And then we got password hashes, the high-risk binaries. Those are any binaries that we found one of those unsafe function references in. And then we have the third-party components and CVEs. So we're just going to kind of show off the file explorer by clicking into this real quick. So this is the original uploaded image. And so it was called rootfs.bin. Here we're actually seeing it's telling me that it's likely encrypted or compressed. Right now, in this case, it's compressed because we were able to extract stuff out of it. But we can actually browse through the entire file system here and see what it was extracted. So here it was able to extract the entire Linux file system for this device out so that we can navigate through it. And then so here we can see that it did find password hash in here turns out you can just like Google this password hash, and I was able to crack it that way. Didn't even have to like run John or anything like that. So that was nice. But also, like, let's say I did want to run this through John. All I'd have to do is hit download password, and this string 0, so this is like this whole string here, that would download it into a text file for me that I could just like run straight against my password cracking software. So then to move on to high-risk binaries. So here, we'll just take a look at like one of these binaries here. Here we can see that we found a reference to a sprintf call. And it's located at this offset inside of the binary, and it's inside of the main function. And so as like a pen tester, again, this doesn't mean that there's a vulnerability, but maybe like I would want to go and like look closer at this function to make sure things are being sanitized correctly, that there's no user input being sent into that sprintf call, things like that. And then if I wanted to like get that binary directly from this interface, so basically everything links back to the file explorer, so I can just click here and then I can download that binary straight from here. So then we'll go ahead and look at the third-party components. So we identified 3 of these third-party components. There's definitely more third-party components on this device, but they're just like, they need to have regex rules built out for finding them. But here we'll kind of show off. So it found an instance of an embed TLS library. So it found this string here inside of this shared object file, and then the regex rule was able to identify that this part was the version right there. So it was able to like parse out the version from just like the rest of that string. So from there, that's where the watchdog service comes in and is able to automatically identify CVEs that affect this given firmware image. So we just go ahead and look at one of these. Okay, so this CV, again, it found it because of embed TLS 260, and this is some, remote code, arbitrary, code or denial of service buffer overflow thing. So I was able to find that just all based on that regex search system that is looking for those third-party components. And yeah, so just to give you an example of what it would do in the case that a firmware image was truly encrypted. So a lot of times nowadays, you'll find that manufacturers are encrypting their firmware, and then like the update process for when you upload the firmware to the device, it will use some like key that's hard-coded into the device to decrypt it and then like install it on the device. And it's kind of like a sad day for us as like pen testers, because then we have to like get on the actual device. We can't just download the file from the internet. So just to show you what it would look like, right? So here I uploaded this like GPG encrypted file. Obviously it's not going to extract anything from here, and you can kind of just ignore the 2 files extracted because it's counting like the parent directory and then the file itself. But if I go ahead and I look at that, again, it's going to give me that warning based on that Shannon entropy that it calculated that this is probably encrypted or compressed. And in this case, if I uploaded a file and it wasn't able to extract anything, then I can probably go ahead and assume that it's more likely encrypted, right? So that's, oh yeah, and then I also wanted to show an example of a key, since that didn't show up in that exact root file system. So I've just got a number of tests here that I used to test the suite with. So here is what it would look like if you found a key file again. So, okay, so I found this, RSA public key that was hard-coded into the image, and then I can even, either go to the file or I can just directly download this key and then store it somewhere. So that's my tool, and so where I want to kind of take this tool in the future is one of the next things I want to do is I want to build a way that I can automatically, based on all this data that I have, kind of calculate some sort of relative risk score. It'll all be relative, but if you upload two pieces of firmware and it is able to extract them, but on one of them it finds 20 CVEs and another it finds only 2 or something like that. Well, then we could calculate some sort of relative risk based on that. And then I want to build in exportable reporting. Like I said, this is like an idea that came up with as a result of Alan's talk, the last talk given in here. Definitely want to be able to export those software bill of materials. I think that would be a useful feature. And then, just to keep on developing ByteWalk, that fork of BinWalk, and fix bugs, because there definitely are some like false positive bugs that the tool has sometimes, and that will like cause the platform to crash if you upload one of those. And then just develop new extraction techniques and be able to support different types of compressed data. So with that said, you can deploy this tool today at that link. If you have any questions about that, I'd love to answer all your questions, and just get any ideas that you guys have about how you could use this or how you would solve some of those problems that we talked about. Yeah.
So have you considered making like a John plugin for simpler?
We got a mic. Sorry. Yeah.
Hi, so have you considered making like a John plugin for the simpler encryption schemes like, I don't know, DesCrypt or anything like that? So it would be able to run quickly and you'd get a quick result.
Yeah, I think I could definitely do that, like with a limited word list. Yeah, because I think in this example, I think that password would have been in like a pretty easy word list. Yeah. No, that's a great idea. Your pick. We'll get to both of you. Oops. There you go.
Have you thought about integrating with any other debugging systems like maybe IDA or Ghidra?
I've definitely thought about Ghidra or Hydra. I still don't know how to pronounce that. Yeah, exactly. I've thought about that. My hesitation at first was that I was reading and I was just like scanning all of the issues that people were uploading in the tool. And one of the things that I thought I saw is that they only supported Python 2 and not 3.
Yeah, because it's using Jython. But there's another project that's on pip called Ghidra Bridge that does some horrible like shim script that deserializes Python objects over RPC, so you can. It's like some horrendous object, but that if I was going to go down that path, then I'm not saying that necessarily it's the best idea, but that definitely not Jython.
No, I've definitely thought about that. It was just like Radar 2 is the tool like I'm familiar with, and I kind of started some of this development work before it came out. And so, but I would like to integrate it because there are some cases. Radar 2 does pretty good on ARM. MIPS, it has a hard time with a lot of function references. So I've definitely like it'll miss things on MIPS, and there's a lot of embedded MIPS devices out there.
So about your regular expressions, I'm just curious about your philosophy there, whether you're looking for every string that might possibly hit, or whether it might be useful to use something like a Yara approach where you can more place the strings and look for combinations, or what? Yeah,
so I've stuck with Regex at this point. I'd totally be open to exploring something that works better. So what I didn't get into here and what's in that documentation file, that Regex documentation, markdown file, is that so what we saw up there was one of the standard or a simple like Regex rule. So I built out the concept of like searching for a nearby string. So how most of my Regex like searches work is first it looks for something that identifies the program. So if you're looking for like an OpenSSL library, right? First you want to identify that this thing is OpenSSL, and then you want to find the version that's like in that binary somewhere. So I'd love to talk after if like you think Yara would be able to do that more efficiently.
So kind of following up on that question, you mentioned focusing on regex rules to detect version numbers and things like that.
Yeah.
Are there any plans to implement something like file hashes to detect dependencies and versions?
Yeah, so that was like my first thought, but and this is something that kind of came up in the talk before this about the software bill of materials and like how do you identify a software component. And the problem you get into there is a lot of these embedded devices, like they might have the same version of OpenSSL, but they've compiled it themselves. And so any little difference in the compiler environment could cause that to yield a different hash. And so at that point, you'd be like in this like rat race of like trying to like compile a database of like every hash of every library that's ever been, produced. But there could be a hybrid approach, right, where you could use some well-known hashes, right, that might be used across a lot of devices and have that complement the Regex system. That'd be something to think about. Yeah. Any other questions? All right. Thanks. I think I got done super early.
Thanks, Matt.